Hi, I'm Kaiping, a research fellow in National University of Singapore. I'm happy to share our work, PACE, Learning Effective Task Decomposition for Human-in-the-Loop Healthcare Delivery. I will first introduce some background information, including the motivation of PACE. Then I will introduce the overview and the detailed design of PACE. After that, I will demonstrate our evaluation results. Finally, I will summarize in the conclusion. Human-in-the-loop data analysis refers to the data management tasks, which require the participation and involvement of both machine learning models and humans. Human-in-the-loop data analysis is important to healthcare delivery. As in healthcare applications, the accuracy of predictions should be considered as a more crucial requirement than giving predictions to all tasks, for example, patients. As a result, instead of providing prediction for each task, it would be better if the machine can handle easy tasks that it can well predict, and hand over hard ones to doctors for help. In this process, task decomposition is a necessary and important stage, in that it can differentiate easy tasks from hard ones, hence can facilitate the process that the model handles easy ones and the domain experts handles hard ones. Let's look at an example to see what is an easy task versus a hard task. In this figure, patient 1 has an elevated temperature above the normal range and an obvious increase in white blood cell. So patient 1 is likely to have some common infections caused by bacteria or viruses, etc. Patient 2 has a normal temperature and white blood cell level and tends to be diagnosed as unaffected. These two cases are relatively common and therefore are easy tasks to be predicted well by the model. Patient 3 has an abnormal temperature, but without a boosted white blood cell level. The condition is more complex. Therefore, Patient 3 may develop some diseases of the immune system, such as HIV, or may exhibit some other symptoms that are closely related to an increased temperature, such as hypothermia, meaning that Patient 3 may not have any infectious diseases at all. In this sense, Patient 3's conditions are more complex and uncommon. Therefore, it's a hard task that should be handled by doctors. In task decomposition, we decompose the given tasks into the ones that are easy to classify and the ones that are hard to classify, and hand over them to the model and to the domain experts respectively. To achieve this goal, classification with a reject option is a solution. Different from standard classification models, instead of always providing a hard decision, a reject option is allowed for some tasks in classification with a reject option. Its key idea is to reject to provide a prediction for some tasks in order to achieve better performance on the tasks accepted. Among the existing studies in this area, some implement a reject option directly, others focus on studying the theoretical characteristics of the rejection mechanism. Different from them, our objective is to propose a general framework, PACE, which is able to optimize task decomposition for healthcare applications. To illustrate the performance clearly, we adopt a metric coverage plot like this. The x-axis is coverage, which means that how many tasks we will incorporate into our model. In the x-axis, we order the tasks by p from large to small, denoting the probability of the predicted class from the model. The y-axis is the evaluation metric we are interested in, such as AUC. Then in this plot, given a coverage C in the x-axis, the corresponding y-axis value theta denotes the metric value achieved when utilizing the covered tasks as input in the classifier. The tasks in the range from 0 to C are easy ones, which can be handled by the model, while The tasks in the range from C to 1 are the hard ones, which are better to be handled by doctors. Then the aim of our proposed pace is to improve the generalization performance on easy tasks, which in fact is to raise the front part of this metric coverage plot. Now let's look at the overview of pace. Our proposed pace aims to optimize task decomposition for healthcare applications and is two-level. On the macro level, we employ self-paced learning, SPL for short, to select easy tasks for each training iteration. Then on the macro level, we adapt the weights of selected tasks through a weighted loss revision strategy. Let's dive into the detailed design of pace. To start with, pace is equipped with a macro-level SPL-based training. The key idea of SPL is to define a task's easiness in terms of the model's ability to predict its true output. Then, for the SPL-based training on the macro level, suppose we use the standard cross-entropy loss function LCE. We will update the parameters following this formula, where 1 divided by n is the loss threshold for determining whether to incorporate a task or not in each training iteration. So during training, we need to gradually decrease the value of n, such that the threshold of task easiness becomes larger and hence, more tasks can be included in training. Finally, all tasks will be included. On the macro level, pace devises a weighted loss revision LW. For the standard cross-entropy loss function LCE, it can be denoted using the probability of the ground truth class like this. We then define a new variable UGT representing the model's computed result before the sigmoid activation function. In our first strategy LW1, we aim to assign more weight to correctly predicted tasks. We revise the PGT variable by multiplying UGT with the parameter gamma. To explain the underlying rationale for LW1 more clearly, we derive the derivative of the loss function with regard to UGT and plot the derivative function in this figure. The gray curve is the standard LCE, while our LW1 is shown as the red curve. We can see that as soon as UGT exceeds 0, which means the task is correctly predicted, the absolute value of LC's derivative with regard to UGT becomes small. Compared with this, our proposed LW1 assigns a larger absolute value of the derivative, meaning that it gives more weight to the correctly predicted tasks. Then we propose our second strategy LW2, which is to assign more weight to confidently predicted tasks. We revise the loss function in this way, and the corresponding derivative function is shown as the brown curve in this figure. We can see that, compared with LCE, LW2 assigns less weight when UGT is near 0, denoting an unconfident prediction. So relatively, LW2 assigns more weight when UGT is not near 0, that is, a confident prediction. We further fuse these two levels together into pace. Specifically, we iteratively update the parameters W until the stopping criterion is met. In each iteration, given the current parameters, we compute the optimum MT, denoting which tasks should be incorporated in the current iteration. Then we select such easy tasks and compute the corresponding predicted labels. Next, we upload the parameters W with our selected tasks. As for the experimental evaluation, we train a deep learning model for binary classification, and more specifically, we adopt the gated recurrent unit model, GRU, in order to handle the time series electronic medical records, that is, EMR data. We note that, according to our ablation study, our proposed LW1 outperforms LW2 in our healthcare datasets. Therefore, in the experimental evaluation, PACE is the integration of SPL and LW1, that is, our best performing proposed method, and is used to compare with baseline methods. Now let's come to the experimental evaluation. We focus on discussing the experimental results in the NUH-CKD dataset, that is a real-world longitudinal EMR dataset from National University Hospital in Singapore. We refer interested audience to the paper on the experimental results in the public MIMIC-3 dataset. In the NUH-CKD dataset, we studied the chronic kidney disease patients, that is, CKD patients, and conduct the CKD patient deterioration prediction, which is formulated as a binary classification problem. The statistics of the NUH-CKD dataset are shown in this table. We mainly conduct 4 experiments. In our first experiment, we compare PACE with several baseline classifiers that are widely used in practice, including LR, GBDT, AdaBoost, and the standard cross-entropy loss function LCE based on GRU model. We find that PACE can achieve higher AUC values than the standard LCE on the easy tasks, showing the effectiveness of our proposal. Then, compared with LR, GBDT, and AdaBoost, PACE can achieve better performance. We also find that when the coverage approaches 1, PACE and LCE can beat the other baselines, which is mainly due to GRU model's advantage to exploit the time series information in the EMR data. In our second experiment, we compare PACE with temperature-based methods, which also revise the derivative function. To explain the underlying rationale for temperature-based methods, we first derive the probability of the ground truth class and the corresponding loss function. Then, we further derive the derivative of the loss function with regard to UGT and plot the derivative function for different t settings in this figure. As shown, different t settings deform the curves in both directions. We compare PACE with the temperature-based methods with different t settings. We find that in different coverage ranges, the best performing temperature corresponds to different t, which confirms the effect of temperature on model's performance. Also, PACE outperforms all different temperature settings, which validates the effectiveness of PACE in improving the performance on easy tasks. In our third experiment, we compare PACE with temperature-based methods with SPL-based training. Similarly, we vary the temperature settings and compare the corresponding performance with PACE. From the results, we first find that other temperature settings tend to exhibit an advantage over the temperature of 1, which is only SPL-based training on the macro level. This demonstrates that the temperature-based weighting methods are effective in improving the performance. Moreover, compared with the previous results of the temperature-based methods without SPL, the corresponding methods with SPL-based training generally exhibit boosted performance. This confirms the effectiveness of our proposed macro-level SPL-based training. Finally, PACE as the integration of SPL and our proposed weighted loss revision achieves higher AUC values than all temperature-based methods with SPL-based training. This validates the effectiveness of our proposed weighted loss revision over temperature-based weighting methods in improving the performance on easy tasks. In our fourth experiment, we investigate the effects of post-hoc calibration methods on the performance of PACE. As a modern neural network, PACE may not be well calibrated. To elevate this issue, Some post-processing confidence calibration methods are proposed and widely applied to supplement models' prediction results with a calibrated confidence measure. In this experiment, we illustrate the reliability diagrams of PACE before and after calibration based on several representative post-hoc calibration methods, including histogram binning, isotonic regression, and plot scaling. We also show the expected calibration error, that is, ECE in this figure. The smaller ECE is, the better the calibration method performs. From the results, we can see that calibration methods generally manage to improve the performance of PACE in terms of ECE. Specifically, plot scaling is the best performing one in this NUH-CKD dataset. These findings confirm the effectiveness of the post-processing methods in calibrating the predictions of PACE and supplement useful auxiliary information to PACE in healthcare applications. This is highly helpful to clinical decision-making, in that PACE can hence better differentiate easy tasks and hard tasks, which can be handled separately by either machines or humans. To summarize, in this work, we identify task decomposition, which is a critical stage in human-in-the-loop healthcare delivery. Then we devise a general two-level framework PACE to learn effective task decomposition for healthcare applications. Specifically, we select easy tasks adaptively during the training process on the macro level, and we reweight the loss for each training task based on its difficulty on the macro level. The experimental results show that PACE can substantially improve the generalization performance on easy tasks. Thanks for listening.